There cannot be many lovers of the Mini who've not heard the name Cooper S, even if they've never had the pleasure of owning or driving one. It's a legend in its own time. When first introduced in 1963, it took the motoring world by storm. A tiny, innocent-looking car capable of taking on the best and beating them. Such astonishing performance didn't just happen. It was the creation of great names such as John Cooper, Paddy Hopkirk, the late Daniel Richmond, and Janspeed Engineering, subsequently the largest tuning company in Europe, was involved right from the start, under this man, Jan Odor. Janspeed's early reputation was built on a series of Minis that turned the world of saloon car racing upside down. From there, through Datsuns, Fords, Toyotas, and each succeeding generation of the mighty Isigoni's brainchild, shelf loads of trophies have followed. A team of experts spent many hours discussing the most viable modifications for this project to remove the guesswork of the inexperienced performance engine builder without access to professional engineering facilities and expertise. To help us show what can be done, we acquired this 73 Mini, which at some time in its checkered past had been owned by an enthusiast. It had many parts on it that we need for high performance already fitted. Once lifted out and cleaned, the engine should be stripped for checking. As it happens, our beat-up old project car had a genuine Cooper S engine in it, the crank being the nitride-hardened EN40B item. Because the bodywork of our project car was a little on the rough side, it was evident that major surgery would be required to remove rust-damaged areas. To facilitate this, the car was stripped to the basic shell, starting with the removal of the front and rear subframes. The basic body shell was then taken to Auto Engineering, who are experienced at body restoration. A new floor section is used to make good the large section removed. In a similar fashion, new panels are installed where rusted ones have been removed. It's important to position the panels carefully before finally welding in place. In our particular case, this is very critical as major panels have been replaced and the look of the car must be recreated. Now, here's our first move towards performance. We're going to reshape the valves. Many hours on the flow bench testing port configurations have shown that most standard valves are forged for ease of manufacture rather than performance. Most A-series heads benefit from bigger valves, but to get the best from any size, the combustion chambers must be reshaped. To avoid seat damage, we're using dummy valves located in the chamber. We can now turn our attention to making the ports flow as efficiently as possible. In this shot, we've blued the seat so you can see how the port is being shaped in relation to it. Unfortunately, porting is an area where many head modifiers believe it is polish that produces the desired results. This is not the case. It is shapes developed from the flow bench and dyno that produces results. The polished finish you can see on Janspeed heads is merely a byproduct of quality workmanship. At Janspeed, we use this special precision machine dedicated solely to cutting valve seats. We are now at the point where some selective assembly procedures can be started. As a final measure, to ensure near perfect valve seal, the valves are lightly lapped into their respective seats. After lapping in the valves and thoroughly cleaning all components, the head can be finished, assembled, ready for use. With the assembly completed, David Vizard tests our modified head on the Janspeed flow bench. The reading shows a substantial increase in airflow, which will translate into more horsepower. Meanwhile, in the body shop, the restoration of our Cooper S lookalike Phase 2 car is coming on. The basic shell is now 100% sound. All rusted areas have been replaced with new panels, and the shell is ready for the low-bake spray booth. Having established that the block for our Phase 2 engine rebuild is sound, it's rebored to accept the new oversized pistons. After boring to about 2/1000ths under the required size, the bores are finish honed to produce not only the correct size, but also the correct finish. Without proper attention to finish, ring seal and life can be seriously hampered. In a high output engine, it will be necessary to utilize special high performance pistons, such as produced by DG Race Products and Omega. A heavy flywheel may make for a smooth idle, but not a responsive engine. Lightening the flywheel or any of the internal components doesn't help static power, but it does help the power available during acceleration. Some crankshafts can be improved and toughened by a process known as tuft riding. All cranks can stand some form of modification, either in terms of lightning, tuft riding, or shot peening. Lightning crankshafts, especially 1275s, can be an expensive business though, and generally only proves cost-effective on engines where the sole intent right from the start is maximum output. Once any lightning has been completed, all the rotating parts must be balanced. This will require the services of a company like Saunders Engineering. The procedure for rotating components is to balance each part independently. That way, parts subsequently changed, so long as they're in balance themselves, will not adversely affect the overall balance. Though any excess weight in the engine can be considered a bad thing, it's especially bad to have excess weight in the connecting rod department. Connecting rods must not only have the same overall weight, but also be balanced end for end. Of all the parts that require balancing, the pistons are the simplest to deal with. Once the heaviest to lightest pistons have been found, metal is removed from the heavier pistons to match the lightest of the set. With parts of the new motor painted, we can start the assembly. The crank should spin freely, as you see here, but professional engine builders will check crank clearances with a dial gauge measuring in thousandths. They will look at end-to-end clearances and then vertical clearances. These must all be within manufacturer's tolerances. For our project car, we made a cam selection based on the latest technology utilizing the high lift, short opening period concept. A Kent Megadyne 266 cam was used, together with Titan 1.5 ratio roller rockers. The short timing gave excellent road manners low down, but the lift, which is higher than race cams of just a few years ago, gave top-end results rivaling some of the milder race cams of that time. This now leaves us in a position to check and set, if necessary, the alignment of the Kent cam's adjustable cam sprocket. Our next task is the press fitting of the pistons to the rods. This is best left to a professional. A number of methods are used. This is just one. After fitting, the pistons should be as free as this. Ring gapping is an important procedure that should not be rushed. Note how rings are set square in the bore with a piston. Best power is achieved with a minimal width ring gap as recommended in the overhaul manual. Provisionally fit the timing chain so the dots are aligned as you see here, while the piston is still on top dead center on number 1. Check cam end float. Our new modified head is almost ready to be installed. Now for the valve train. Here you see a close-up of the Titan 1.5 ratio roller rockers ready to go on our engine. Turn the engine over and ensure the rockers are sitting correctly in the pushrod cups. Then torque to manufacturer's specifications. Check and adjust valve clearances. A high-performance cam can only deliver its full potential if it's correctly timed in. A stack-up of manufacturing tolerances can easily put the cam timing out by up to 6 degrees. The timing process you see here would eliminate such errors. Many find this complex, but the exact procedure is fully explained in Tuning BL's A-series engines. Once the magnitude of any error is established, the adjustable timing sprocket can be reset to cancel out such errors. With the completion of the cam timing, the oil slinger timing cover and crank damper can be fitted, as can the distributor drive gear assembly. First, the oil pickup. To prevent loss of oil pressure during hard cornering, a central oil pickup of the type shown here must be used. With the various close ratio gears, drop gears and final drives available, many combinations are possible. With the aid of an assistant, the box is mounted on the engine. This allows us to check that seals have not moved during assembly. On high output engines, flywheel fretting can be a problem. This can be largely overcome by lightly lapping the flywheel to the crank with fine lapping paste. Here is a lightened flywheel ready for fitting. The spaces indicated here mechanically compensate for the amount of metal removed. To cope with the added power on bigger engines, it is advisable to use a heavy-duty clutch. Usually, a rally spec disc and cover is more than adequate. We rejoin work at the paint and body shop with the interior painted. The 2-pack acrylic colour is applied in 3 coats and then baked hard in the oven for approximately 40 minutes. The car is then unmasked and the final reassemble of all internal and external fitments is made. All underbody panels are treated with full underseal protection. The fitted wheel arch extensions are filled and the screw heads are match painted. When fitting new body panels, the car is established back to original specifications. The distributor for our high output engine is taken care of by this Luminition-equipped Cooper S distributor with the appropriate advance curve. Eliminating points and utilizing state-of-the-art plug leads and plugs ensures the best possible spark performance. The main engine assembly can now be lowered into the car with the installation procedures simply being the reverse of removal. If multi-throat carburation is to be used, best results are achieved with the longest intake consistent with bulk head clearance and a no-compromise filtration system. For this, a Janspeed dual-function manifold mounting SUs and a high-flow K&N filter were used. After running in, the car should be set up on a chassis dyno. Comprehensive instrumentation allows detailed fault finding and accurate carburetor and ignition calibrations under loaded conditions. Now's the time to upgrade the suspension to allow the most to be made out of the engine's higher output. By shortening the suspension trumpets in a ratio of 1:5 at the rear and 1:3 at the front, the car can be lowered. However, an easier route is to use the Ripspeed adjustable high-low suspension, as seen here as part of a complete suspension package. New bottom arms will be needed to change front wheel camber angles to cut understeer. Adjustable rods allow steering caster angles to be changed to suit your requirements. In a similar fashion, adjustable rear camber brackets can be fitted to allow optimum angles to be achieved. To complete our package, a set of adjustable Coney shocks, set at half hard, are fitted. With the adjustment facility, the suspension was set with 1 degree of negative camber. While on a flat floor, this optical tracking gauge is used to set the steering to the desired geometry. To cut what little body roller Mini has even further, this rear anti-roll bar can be fitted. On our project car at least, the fitting of the anti-roll bar was the final job, so now is the time for a road test. Rally cars and their circuit racing counterparts represent a very specialized form of engine building, and although we learn many lessons from competition, modifying a civilized high-performance road car is a science in its own right. Hopefully, we've shown you something of what goes into building such a magnificent machine. So there you have it.